Thank you. Thank you for inviting. Thank you for coming. It is always very nice for me to be back to UCLA. I love the campus and I miss it. It's very cold up there. Can everyone hear me at the back fine? Okay, cool. So let's begin. If you're interested in understanding why neural networks work well, how should we make them work better? There is really two key questions. The first one is why can we train them relatively efficiently? We know that they are very large models, so millions of weights, billions, if you look at it, look at what is going on now, trained on many samples, almost proportionally as many samples, with an objective which is clearly not convex in both the inputs and the weights. So really, we shouldn't be even allowed to train these kinds of models. Non-convex optimization in 10 dimensions is hard. It doesn't make any sense that we are doing it in millions of dimensions. This is the kind of question that I was asking during my PhD, and the rough thesis of my work, of a lot of work by many other people, is that the loss functions of neural networks are non-convex, but they are rather benign. You should think of it as when you go hiking in the Grand Canyon, it doesn't really matter where you begin. There is always the Colorado River below you, right? It doesn't matter which part of the river you want to fall in. It's the same river. So in some sense, the landscape is hard, but not very hard. And this is kind of why we can train them well. Okay. The second question is why do they generalize so well to new data? In high school, people told you that if I give you 10 data points, you shouldn't be fitting a polynomial of degree 15 to it because it will be very wiggly in parts where you do not have data. Deep learning loves doing this, and somehow we do not seem to get hurt by doing this. So something must be different in the kind of problems that we are solving today than what they told you in textbooks. Right? These are the two big questions which I'm interested in answering. Maybe we should also think a little bit about why. Okay, I will give you two reasons to answer these questions. The first one is just a matter of pride. You know, like the textbooks have told us something. We see stuff that clearly doesn't conform to what the textbooks told us. Either the textbooks are wrong, or we maybe did not study these things as well as we think we studied them in textbooks, right? So clearly something doesn't fit right, and we would like to resolve this for the purposes of completeness, if nothing else. And the second reason, I think, is a bit more important. And I believe, and I hope to convince you at the end of the talk, that the success of deep learning is telling us something new about the nature of data. And this is why it behooves us to ask these questions and understand these questions. We would like to know new things about how data looks like in the real world. Okay. Let me show you, to set the context, I'll give you I'll show you two results. These are mine. There are many similar results in the literature. Deep networks are full of peculiarities. This is one. So a few years ago, at this point, we found that when you train typical neural networks with SGD, stochastic gradient descent, you end up in regions that are rather flat or rather wide. So if you calculate the second order expansion of the Taylor series, the Hessian matrix, which defines the curvature of the loss function, you will see that the Hessian matrix has eigenvalues that are very many of the eigenvalues of the Hessian are nearly zero. That tells you that in many directions, 95–96% of the directions in weight space, the loss function doesn't change very much if you move a tiny distance away from where you are. Okay, and this was quite surprising because analysis in statistical physics or learning theory will kind of convince you that such regions are not common. Such regions are very rare in this gigantic energy landscape, gigantic space of weights. And not many regions should be like this. It should be very hard to find such regions. SGD seems to find them all the time. In fact, when it doesn't find such regions, when it converges to regions where the loss function is not as flat, it doesn't seem to generalize as well. Okay, this is just an empirical fact. And so we said, okay, we know that SGD typically finds such regions. Let us go about optimizing different objectives. So if f of w is the trading loss, that you are minimizing with SGD. I was minimizing objectives of this kind. It is a smoother version of the original loss. G sub gamma is a Gaussian kernel of bandwidth gamma. And it doesn't change the locations of the solutions much, but it does make the energy landscape less rugged. Okay, and these algorithms work quite well. They are still pretty fast at training neural networks. But the fact of the matter is that wide regions are not very common in the energy landscape, and it doesn't make sense that you find them so often. Here is a second example. We noticed that the noise in stochastic gradient descent, the noise comes from you taking mini batches as opposed to the entire calculating gradient of the entire data set. So the discrepancy between the stochastic gradient and the full gradient, calculate the variance of this particular quantity, and you'll get a big matrix whose size is number of weights times number of weights. A priori, this matrix doesn't need to have any structure. We notice that it is typically very, very, very low rank. And that tells you that when SGD moves, the noise in stochastic gradient descent, it doesn't allow it enough equal freedom in all directions. There are some directions in which you're moving basically because of gradient descent, and a very small fraction, about 1% or less than 1% or so of the total number of dimensions, is the regions where noise allows you to move. Now, in physics or in statistics, such things are not very common. A physicist would call such a system a non-equilibrium dynamical process because it doesn't have detailed balance. When you move in one direction, you're not allowed to come back in the same direction with the same in the opposite direction, the same probability. And this leads to somewhat exotic phenomena. For instance, we showed that you can converge to regions that are not the critical points of the loss on which you're taking mini batch or gradient updates. And that is silly. You are minimizing an objective, and I'm telling you that you converge to a point which is not even the critical point of the objective that you're minimizing. Okay, you can have infinite loops of trajectories. The weights never really converge. They can evolve in a subspace where the gradient of f is non-zero, but the gradient of some other function phi, we don't have to worry about it. What that function phi is right now is zero. So these are very, very exotic phenomena, even if by the standards of biology or physics. You do not often find systems that exhibit such patterns. Deep networks do. So this is just two kinds of peculiarities. Okay. Now, what I want to say is that this is related to the Hessian matrix. The noise in stochastic gradient descent is pretty close to the Fisher information matrix, up to a rank 1 difference and up to the empirical Fisher matrix. And this is what I want you to keep in mind. Two somewhat surprising phenomena related to the Hessian, the second related to the Fisher. Okay. What I want to convince you in the rest of the talk is that over the years, we have attributed a lot of mysterious properties to neural networks in our effort to understanding them. But there is an elephant in the room. So if you go around different explanations for why neural networks work, some people will say, oh, there are so many parameters as compared to the number of samples. The over-parameterization should clearly be the key reason that distinguishes neural networks from other machine learning models. Maybe that explains why they work well. If you ask a very simple-minded question, if I have too many parameters and not enough information in the data set to restrict or constrain all these parameters, then why the heck should they matter? Right? This shouldn't really affect my predictions because I'm not constraining them. So that couldn't be a complete explanation for why things are working well. If you ask some other people, they'll say, oh, the inductive bias of architectures is very important, and that is what we should study. Well, in 2014, 2015, everyone was very happy that convolutional networks started working well because we believe that the filters look similar to what people have seen in the visual cortex. 2-3 years ago, transformers work equally well, and these are totally different inductive biases, no a priori relation between the two. So clearly that cannot be the only story in the town. Okay, and we can go around the room like this and attribute let's say gaps in our understanding corresponding to each of these lines of attack. My contention is that the elephant in the room is simply the structure of the data. Data that we typically feed neural networks has very, very peculiar properties, and a lot of things that we see on the outside after we study these fitted models are probably coming from us not knowing what the data looks like. And so this is how I would like to think about this research. And let me explain to you one result. This was presented at ICML last year. Focus on the blue line for a second. The blue line shows the principal component eigenvalues of CIFAR10 images. CIFAR10 is a data set of RGB images, 32 cross 32 pixels. So that's 3072 dimensional data. I string up every image as a column of a matrix, and now I have a matrix of rows 50,000, which are the number of training samples, and columns, which is 3072, which are columns which are 50,000 and rows which are 3072, which are the dimensions of my input, and I calculate the eigenvalues of this matrix of XX transpose. Okay. People in computer vision have always believed that natural images lie on low dimensional manifolds. This line tells you that they don't exactly lie on a low dimensional manifold, at least not in this linear sense, but it lies on an effectively low dimensional manifold. The difference in the largest eigenvalue and the smallest eigenvalue here is about 7-8 orders of magnitude. So if you try to visualize how the point cloud of images looks like for CIFAR10, it's a long ellipse, which is very, very, very long. It's 10⁸ times longer than the thinnest dimension of this ellipse. Okay. And this is really the effective dimensionality, if you will, 100 dimensions or so, not much more than that. Okay. This is just a fact about data. You can do it on your laptop in 5 minutes, nothing special. What we showed is that if data looks like this, then essentially any quantity that you can calculate inside the network. The green line are the eigenvalues of the Hessian matrix of a trained network. This is a large residual network. And this has about 3 million weights. So we calculated about the first 2000 eigenvalues of the Hessian. It's expensive to calculate these matrices. The orange line are the eigenvalues of the Fisher information matrix of the trained model. Again, in this case, it's a tiny bit cheaper to calculate. We did 3000. Okay. And you can go, you can look at many other quantities. For instance, the purple one are the eigenvalues of the correlations of activations of different layers. The red line are the eigenvalues of the correlations of the Jacobians of different logits. Okay. And there are many such quantities. When data has this peculiar shape, it drops quickly at the beginning and then slopes linearly on a log scale. Then these matrices also seem to have eigenvalues that look like this. Okay, this is a result from this particular experiment. I'll show you a little bit about the theory later. Let us ask ourselves why this is interesting. Focus on the orange line and let us look at an eigenvector that lies somewhere deep inside the tail. This eigenvector gives us a direction in the weight space where I'm allowed to perturb the weights by 7-8 orders of magnitude before I see any appreciable change in the output of the function. This talks about a gigantic redundancy in how the parameters of this model are being used to make predictions. We call such shapes or such eigenspectra sloppy. That's because the network had 3 million weights to use to make predictions on this particular data. It chose not to use all of them. It chose to use only 100, 150 out of those degrees of freedom. These are not just raw parameters. These are combinations of parameters. So 100, 150 linearly independent combinations of parameters. And then it chooses to use all the others in tiny, tiny, tiny ways. Okay. These ones are the ones that I'm allowed to perturb by really gigantic distances before I see anything, any change in the output of the function. Now, if you think about it, the head of the eigenspectrum, the head of the blue line, corresponds to things that are very salient. So this is a picture that I took from Plato's theory of forms. So the end points of this axis are the purest cats and the purest dogs and this stuff that is canonical. The tail consists of things that are aberrations. So for instance, blue sky, which doesn't change very much across images, blue dog, which is very rare in many images. Yes. Yes, so this is close to Marchenko-Pastur, not exactly that. A spike would have a big eigenvalue at the top, and then now depends on what exactly your ensemble is to get the eigenspectrum. These kinds of plots so this result is the blue line is not that different from the classical result signal processing, which says that the power in frequencies decays as 1 over f square in natural images. At high frequencies and small amplitudes, it becomes pretty difficult to distinguish between a power law decay and an exponential decay of this kind. So this part, you can take it with a grain of salt, but this part is pretty clear that it decays quickly. Okay. Okay, so this is a fact about data and a network trained on this. Now, what I would like to say, or what I would like you to think about is if noise were to come and perturb this part of the spectrum, then it wouldn't change anything. It wouldn't change the output of the model. So neural networks are resilient, or neural networks fit well, not because there is anything special inside the neural networks, but because the inputs are sloppy. I haven't told you yet how the outputs depend on the input. The outputs can depend on the inputs in slightly non-trivial ways. One experiment, this is a preliminary result that we have now, is the outputs typically also depend only on the salient aspects of the input images, and they depend very weakly on all the other aspects. Okay, and that tells you that you're making 95% of the predictions or 95% accurate predictions by fitting the early parts of the spectrum, and the rest of it is decorations. Rest of it is embellishments of the accuracy, which we did not have 5 years ago. Now we do. And that doesn't change the fact that we, or that doesn't hurt us from, that doesn't hurt in the sense that we can overfit. Okay. So many systems are sloppy. Sloppiness doesn't seem to be something peculiar to images. You can also see it in text and sounds. It doesn't seem to be peculiar about neural networks, but many other systems are. I'll give you one example. So this is a mathematical model of an extracellular kinase, regulatory kinase called ERK half. And this is correlated to growth of certain cells, PC12 cells in rats. Okay, and it can be activated by these two particular proteins. One of them is called EGF, epidermal growth factor, and NGF, which is neural growth factor. And depending on which one you stimulate the cell with, for instance, if you have EGF stimulation, then you will see that the ERK kinase spikes a bit. So it has transients. If you stimulate the cell with NGF, then you will see that ERK increases to a large magnitude and stays there. And that causes cells to differentiate when they grow. And EGF causes cells to increase in the number of in the populations. It causes them to proliferate. The fact of the matter is that this is a system that is related to how cells grow and how they are activated, this particular growth patterns. For us in this room, you can think of it as a system of ordinary differential equations. The output of this system is the concentration of ERK half, for instance. The parameters of the system, you can think of it as the rate constants of all these reactions or the concentration of proteins that form this reaction, whatever you want. You're allowed to calculate the sensitivity of the output with respect to the parameters of the system. Okay, the Fisher matrix is Jacobian transpose times Jacobian. Jacobian tells us how sensitive the output is to the parameters. These are the eigenvalues of the Fisher matrix of a model, of a nonlinear regression model fitted on data of the system, and took it from this paper. Again, the eigenvalues are spread essentially uniformly across a very large range. Now, when a biologist sees this picture, they are very happy. They say, of course, we know that biology doesn't like to rely on all these very many degrees of freedom. It is sensitive to only a few degrees of freedom, so that when someone else comes and deletes those degrees of freedom or affects those degrees of freedom, the function of the cell is not ruined. Okay, so this is a post hoc explanation for why this system is sloppy and why it helps its behavior. A pretty cool thing that we are trying to explore right now is why would the system become like this to begin with? It's an evolutionary argument that says that when a system tries to track changes in the environment, it has to become sloppy because the environment can change in many ways and you have to be insensitive to all those changes while still preserving function. Okay, so this is one instance where a system in nature is sloppy. You can go about and you see many different examples. So an Ising model is a very classical model in statistical physics, pretty little to do with real systems. It's a model where you have spins that are correlated to with each other depending on how your neighbors between the depending on the coupling constant between you and your neighbors. If the coupling constant is positive, you and your neighbor like to both point up. If it is negative, you like to point in different directions. The probability distribution of these spins is a function of these coupling constants. It is a very insensitive function of these coupling constants because the eigenvalues of the Fisher matrix again are spread over very large instances. Okay, so many systems are sloppy. Now you can study the model of these systems, which is what this particular picture is about. In the previous case, we tried to argue that if the input data is shaped so and so, then the model becomes sloppy. Okay. Let me explain this result to you. So as I said, we showed that if input data that you feed to a neural network have a spectrum that decays quickly, then the Fisher matrix or the Hessian matrix also have a spectrum that decays very quickly. We cannot show this sentence exactly, so that is why I put a little tilde in that. What we can show is that the trace of the Fisher or the trace of the Hessian are upper bounded by the trace of the input correlations. So if the input correlations are small, then the trace is small, and there is a term that is dependent on the number of on the magnitude of the weights. And the way to interpret an inequality like this in this context is that suppose I force the weights to lie within a ball, so I can upper bound this entire quantity by some constant. Now, and I take the network and stretch its size and make it very large. So the number of terms on the left-hand side keep on increasing. The trace is a summation over all the eigenvalues. So the number of terms keep increasing. The blue term, of course, is a constant. So that eigenvalues at least have to decay. We don't know yet how they decay, the pattern of the decay, but they at least have to drop down. For models that are infinitely wide neural networks or inner product kernels, you can get an exact result that says that the spectrum of the Fisher matrix is controlled by the spectrum of the input correlation matrix. If you kind of dig down a little bit, you can show a slightly stronger result where we took one layer and you look at the particular block of the Fisher matrix of weights on that in that particular layer. And this is a quantity which we define called the spectrum of the correlations of activations of that particular layer. And the spectrum being simply a sequence of the eigenvalues. The sequence of the eigenvalues of the correlations of that layer is upper bounded by the sequence of the eigenvalues of the activation of that layer. This is the particular block in the Fisher matrix. These are the this is the spectrum of the correlations of the activations. So this doesn't tell you that the entire spectrum of the Fisher matrix is dominated by the correlations of activations, but it tells you a layer-wise result. So if the activations are sloppy, which they seem to be in experiments, then the blocks of the Fisher matrix should be sloppy. If the you can write down a similar result for the Hessian. So it's not quite a complete result in the sense that we cannot show exactly that sloppy inputs implies sloppy Fisher, but you are kind of there. Let me show you one application of this result. People in learning theory like to write down inequalities of the following kind. So this is what is called a pact-based bound, and they will say, let me create a probability distribution on the space of hypotheses. Let's imagine that this is a space of weights for here. Little e of q is the test error of a hypothesis drawn from randomly from this distribution q. E hat of q is the error of such a hypothesis on one of the samples in your training set. You choose q however you will. I will choose to draw samples on the test set or the training set, and now I'm calculating little e of q and or e hat of q. You will get inequalities that look like this. The probability of you making a mistake on a test datum for a hypothesis drawn from q is upper bounded by the probability of you making a mistake on the training datum plus some complexity term. The complexity term takes the following form. The P is not important. It is just a prior over the space of hypotheses. But it depends on how many different hypotheses Q puts its probability mass on. If Q puts its probability mass on many hypotheses, then I find it difficult to pluck one good hypothesis out of them that has a good tight bound. And that is why this is, lies in the numerator. So the way a learning theorist would interpret this inequality is if Q puts its mass on many hypotheses, then you should give me requisitely large amounts of samples to distinguish between all these many hypotheses. Otherwise, I cannot give you any guarantees of what the test error will be. The probability of making a mistake on the test statement could be. Now, over the last few years, people noticed that when they started plugging in numbers into these inequalities, things didn't quite make sense. Typically, in deep learning, the training error is quite close to zero. So we can just set this thing to be zero. Typically, if you take a simple problem like MNIST or so, the test error is not more than 5%. This particular stochastic test error is not more than 5%. So let's call it 0.05. But the complexity term is much larger than one. It may be like 100 or 1000 for typical models. Now, it doesn't, you don't need to write down a theorem to convince me that the probability of making a mistake on something is less than 1000. It's obvious, right? So that is why people have been very anxious about these bounds being vacuous. This is, it's there's nothing wrong in how the bound is derived. It is just a mistake in how we're applying it, okay? What we showed in this paper is that we can give an analytical non-vacuous bound on the test error of general neural networks. I can just write it down. It is related to the eigenvalue of the Hessian matrix. That is not vacuous. So for instance, for a 3-layer network on MNIST, this is rather small, the right-hand side of this particular thing is about 0.38. The VC dimension would be very large. It is about 50 million, more than 50 million or so. Yeah. So this is the analytical bound is of course not tight, but at least it is not vacuous. You've brought it below 1. In the paper, we have also developed a lot of sophisticated numerical tools to get basically tight bounds on the generalization error of generic neural networks. Instantiating these algorithms for networks that are quite large is hard. But that's just a problem of like instantiating the algorithm. The mathematics works. Okay. So we do not need new theory to understand neural networks. We just need to understand the existing theory a bit better and apply it with the appreciation of the fact that the data that we have at our disposal is not arbitrary data. It doesn't come from a nice big isotropic Gaussian. It has a peculiar structure. If the data is sloppy, the Hessian is sloppy. If the Hessian is sloppy, then the bound works. Questions? Okay. Here is another example, another application. If you look at the calculations, you can pluck out a quantity that we like to call the effective dimensionality of a neural network. It goes as follows. So the effective dimensionality, which is the stuff on the left-hand side, is the number of eigenvalues that are larger than this threshold. The epsilon is not important. It's again related to the scale of the prior, but the denominator is kind of interesting. The number of eigenvalues that are greater than epsilon divided by 2n minus 1. So if I give you an infinite number of samples, you are looking at the entire dimensionality of the neural network to fit these infinitely many samples. If I give you few samples, then the effective dimensionality of the network, which heuristically you can think of it as simply the elbow of this particular plot, and this is the effective dimensionality. This is how it shows up in the packed base bounds. It is the number of dimensions after which the packed base posterior has to pay attention to the prior, and before that it pays attention to how quickly the loss changes in those directions. Typically, the number of constrained degrees of freedom in a trained neural network is as small as 0.5% of the number of weights. So when we train models with millions of weights, we are really training models with degrees of freedom that are more like 5,000, 10,000 or so. Okay, and it shouldn't be that surprising that we can get good test error with 100,000 samples, 200,000 samples for typical problems. Okay, the deep networks look very large on paper, but secretly they are quite small. And that shouldn't be surprising. So we are not feeding enough data to restrict all these parameters, and obviously they're not restricted. This is just a way of calculating how many of them are not restricted. Yes. The Yes. So you can think of the pack-based posterior as a probability distribution around your trained network. Now I would like to expand this posterior. I'm allowed to expand it in directions in which the loss doesn't change too much. The training loss doesn't change too much. If I expand it in the directions in which the loss changes too much, then my test error is also going to be bad. So these are really like the dimensions in which the posterior gets to spread out. Not spread. Epsilon is something, yes, epsilon is different for different architectures. The way these bounds are calculated is that we calculate a union bound over different epsilons. So it's a search mechanism to get a tight bound on the right-hand side. Okay, so here is a mental picture for how the space of predictions of a neural network is. I also showed in the paper that typically when you train, you're making changes to the weights that are in the stiff subspace of the Fisher matrix. So calculate the Fisher matrix at initialization, and you're moving in a subspace that is essentially the stiff eigenvectors. And these are the stiff degrees of freedom that are learned by the model. These are the ones that if you do perturb them, you will see non-trivial changes in the loss. There is many other degrees of freedom that you're not worried about fitting. This is 99.5% roughly. That we call the sloppy degrees of freedom. These are the small eigenvalues of the Fisher, if you will. Those degrees of freedom you do not fit because you did not reduce the learning rate enough, because you need to reduce the learning rate to solve these very ill-conditioned optimization problems. But it doesn't matter, because they affect the accuracy in tiny, tiny ways. These are the degrees of freedom that affect the accuracy a lot, and those are the ones that you better fit. Okay, so this is a cartoon in my head. The manifold of predictions of the network might look a little bit like a hyperribbon. So it is very long in some directions in which you're moving in, which are the stiff degrees of freedom that you're fitting. And the other degrees of freedom, they don't change very much. So if I look at the behavior of the model as a function of the weights, the behavior is very insensitive to the sloppy degrees of freedom. And it's very sensitive to the stiff degrees of freedom. That is the picture. Okay. Over the last year or so, we have been basically making this picture more and more rigorous. This is the subject of two papers. The first one will be presented at ICML in a couple of months. The second one we just put out on arXiv, and I'll explain to you this result next. Okay. The thing about this is a neural network is a probabilistic model. We have weights W that can be represented as a likelihood of y given x. Y are the outputs, x are the inputs. A priori, this is an infinite dimensional object. Any x that I plug in, I get one number, and that is what makes it quite hard to understand it. So it's a very large object, and the weights create the likelihood in very complicated ways. So it's not very easy to understand the weights and say something about the likelihood. And this is really the root trouble in all theoretical analysis of deep learning. We have been playing a pretty cheap trick, I should say. We think of this object. So if you want to understand a function and you did not take a class in function analysis, then let me measure the function at a finite number of points and then pretend that this is the function. It's a long vector of all the measurements of the function at these points, and I will forget the fact that it's a function and treat it as a vector. Okay, so we will measure this function at the n samples in our training set, which are all the images in the training set. If you are talking about ImageNet, n is, let's say, 1 million. For each of these images, I have 1,000 predictions that the model makes, 1,000 different classes, so 1,000 different probabilities p of y given that particular x that I have, right? So together, this is a billion dimensional vector. 1,000 images times 1 million images times 1,000 outputs for every image. And doesn't matter what your architecture is, doesn't matter how you trained it. If your network predicts the exact same 1 billion dimensional vector, then there is nothing to distinguish that network from some other network, right? This is the probabilistic model we have at our disposal. What we are going to do is put some landmarks in this space. It's a huge space. One point in this space is special. This is the true model, the one that predicts the cat to be a cat, the giraffe to be a giraffe, etc. So 0, 1, 0, 0, 0, 1, 0, 0, 0. These are the outputs of the model. And that is the true model. Okay. Typically, when you begin training, neural networks are initialized to predict a uniform distribution over the classes. So 1/1000, 1/1000, 1/1000 for every image, for every class is what the network typically begins training from. So the name of the game in training a neural network is to begin at this point that we call ignorance, and then go to some other point that we call truth. The problem is that you're living in a billion dimensions, and there's many ways of going from one point to the other point in these many dimensions. Okay. We can, once you have defined a space like this, we can also define distances in this space. We like to use a distance called the Bhattacharya distance between probability distributions for the following reason. So if you have a vector space or a space with a billion dimensions, essentially any ways to compute distances between points goes to hell pretty quickly. Hellinger distance will be will saturate very quickly, and there is really not much you can do to pluck out the geometry of the space by looking at distances. Quantities like the Bhattacharya distance, which you can think of it as the square roots of the probabilities lie on a sphere, because probabilities sum up to 1, so the square roots lie on a sphere of unit norm, and this is the inner product between those two such vectors on the sphere. The logarithm here allows this distance to be well behaved, even when n is very large. If I wrote down the formula for the Hellinger distance, you will see a big product over the number of images, and that is why it will saturate very quickly. The Hellinger distance is a metric. Bhattacharya distance, or the symmetric Kerr divergence, which also has a logarithm, which also does not go bonkers in high dimensions, are not metrics, they are distances. So they violate the triangle inequality. And so we'll fall into a lot of grief while interpreting this analysis, because we are working with things that are not metrics. Okay, so, and I'll explain it to you as we go along. But now we have a simple thing to attempt. We would like to train lots of models, like hundreds of thousands of networks, and look at the geometry of the space that they explore during training by computing a multidimensional scaling of these points. So for those of you who who don't remember MDS, principal component analysis preserves Euclidean distances between points in the original space and the new space. Multidimensional scaling can be used to preserve some other distance, in particular the Bhattacharya distance between points. Okay, so we'll train lots and lots of models. We will embed them into a lower dimensional space to preserve the pairwise Bhattacharya distances, and then we'll study the visualizations or study how the embedding looks like. Okay, now one trick that we do is typically in bioinformatics or so, when people use MDS a lot, they will throw away negative eigenvalues. If they have distances that are not metrics, they will get negative eigenvalues and they'll throw them away because it's hard to understand them. They have meaning, and I'll show you how they allow us to understand very different things about what the probability distributions do. Okay, so we don't throw them. Our embedding is not Euclidean. Our embedding is has complex coordinates and some Minkowski space in which we embed from high dimensions. So to summarize this slide, it's a little bit heavy. We take probability distributions in a billion dimensions or many dimensions and embed them into lower dimensional spaces, and I'll show you what it looks like. Here is the picture. So P0 is the point where typically networks start training. This is the point where you have predicting 1/1000, 1/1000 for all images. This is CIFAR 10, so it has 50,000 images, 10 outputs for every image. So it's a 500,000 dimensional space. Okay, and these are the top 3 dimensions that I'm showing you out of that. All networks begin at P0 and they end at truth, because they fit completely. Every point here is one neural network, and all these networks towards the end of training, they have 0 error and they are very close to truth. Okay, there is 6 different architectures. There is a fully connected network, a CNN, VIT, which is a self-attention based network, a small nest and a large nest net. Conmixer is basically a convolutional network, but it works on large patches. 6 different architectures trained with SGD, with nested of accelerations and SGD, with Adam, with different batch sizes and different learning rates and different weight decays and different batch normalizations and different augmentation and complex augmentation, lots of variations. There's about 150,000 different networks. that we checkpointed during training. For each of these different configurations, there is about 2,000 different types of networks, okay? Architectures trained with many, many different algorithms. What is surprising is that in this 500,000 dimensional space that you should be traveling in, all these networks, they live on what is essentially a 3-4 dimensional manifold. So the explained stress in MDS, or the explained variance, if you want to think about it heuristically for PCA, is 76% in the top 3 dimensions. The networks, when they travel to truth, they live on a 3-4 dimensional manifold, and all of them live on the same manifold. That's crazy. So a fully connected network and a ResNet, they not only learn the same thing at the end because they interpolate the data, but they also learn the same thing along the way. There is not very much difference in these architectures trained in different ways. They are all rather inefficient. So we can also calculate the geodesic in this space, and they are not tracking the geodesic. The geodesic is the path, are straight lines in metric spaces. So it's the shortest distance between 2 points. In this particular case, the geodesic is easy to calculate because, as I said, if I have a probability distribution that sums up to 1, the square roots of the probabilities, they lie on a sphere of radius 1. So 2 points on the sphere, the straight line joining them is just the great circle. So we can just calculate the geodesic on the product manifold of all these probability distributions. It's an analytical formula. Okay, none of them are close to it. They are all far away from it. Okay, so a few surprising things. The training process explores a very low dimensional manifold, and that tells you a little bit about why training neural networks is somehow tractable. You're training billion dimensional weights, but the intrinsic difficulty of the optimization problem could be this small. Okay, I can write you down this manifold in 3-4 coordinates, and it will be pretty reasonable or a faithful explanation for the entire space of models that you have seen. Different architectures have slightly different trajectories. We'll talk about it in a bit. They're all different from the geodesic, and there's also a spread of points that are kind of away from the manifold. So this spread comes due to different reasons. In the beginning, it is predominantly coming from Nesterov acceleration being little incorrectly initialized. Towards the end, again, it comes because of not restarting Nesterov acceleration, which is what people typically do in deep learning. A lot of the points here you can blame Adam for them. Typically, Adam has trajectories that are very long, and this is probably correlated to the fact that it doesn't work that well for getting generalization errors in computer vision. But we have analyzed the details of this manifold, and we find that we can explain the spread of the points using different algorithms or the deficiency of different algorithms. But each of these points, it represents a model that goes out of the manifold, but it can be made to come back on the manifold simply by training it further. You don't need to do anything special. All these points eventually do get to the truth. Okay, there's just weird wiggliness in how they get there. Okay, so here is the same manifold projected in two dimensions. So this is PC1 versus PC2. And what I want to show you now is the fact that the eigenvalue corresponding to the second principal component is negative. So distances in Minkowski space, you might remember this from high school, they go as delta x squared minus delta y squared if the eigenvalues were both equal. Okay, so if I show you where the truth is, this is ignorance, where everyone begins learning from. Truth lies very, very, very far away from it. There is a line joining truth along a light cone where all points have 0 distances between them. So if the distance between 2 points is delta x square minus delta y square, then there are points that look different to us in a Euclidean sense, but they are really at 0 distance from each other. Okay, so you can imagine drawing a big cone. This is the light cone in special relativity, and all the points along that cone are equivalent to truth. The visualization method is simply stretching them out for reasons that are somewhat mysterious to us also, and we can talk about them later if you will, if you want. But these points are all at very, very small distances to the truth. So when you train a network, you don't exactly minimize the cross entropy loss. You inch closer to it, and you're very, very close to it after many iterations. These are all the points that are pretty close to the loss. Around here, you already have zero training error, and the probabilities are improved and refined by the training process as you go closer to the truth. Okay. To explain why the negative direction is interesting or important, let me give you an example of the Ising model. The Ising model, as I said, is a bunch of spins. Typically, physicists analyze the Ising model using two parameters. Beta is the temperature. How confident you are to go against your neighbor is what the temperature tells you. If the temperature is high, then you don't really care for your neighbor's configuration too much. You take whatever value you want. The magnetic field H is the second parameter, which is a bias applied to all the spins. If the magnetic field is positive, let's say it's pointing up, then all the spins have a larger probability of pointing up. If the magnetic field is pointing down and has a very large magnitude, then all the spins point down. Okay. Now, this is the corresponding manifold for the Ising model. Now it has two parameters, the temperature and the magnetic field. And think about the following experiment. So Ising model with the same temperature and an infinitely large magnetic field is a model where all the spins take values that point up. The same model, I can apply a symmetric transformation to it and make the magnetic field point down, and I'll get the exact same probability distribution up to this symmetry where all the spins point down. So in some sense, there is a symmetry in how different Ising models with a magnetic field of minus infinity go towards zero, and Ising models with a magnetic field of plus infinity come to zero from the right-hand side. At zero, it's the same model, but the friends of 0.01 lie at infinity or are towards infinity, and the friends of minus 0.01 are towards minus infinity, and there is a symmetry between them. So the visualization method that we are using, it's MDS, as I said, but with this funky Minkowski stuff, it chooses, it cannot represent 0.01 and minus 0.01 in this next to each other because the distances are very different across them. So it creates a negative eigenvalue to split them across each other. And this is the reason why things happen. The moral of the story here is that we are plucking out signal from 500,000 dimensions. You can see the differences in the vectors in these dimensions because of the negative eigenvalue. And this is very weird and mysterious. And if you have thoughts about this, let me know. This is the picture of the test manifold. It looks quite similar to the training manifold. Again, it is effectively low dimensional. The explained stress in the first 3 dimensions is a bit smaller than the test stress. This is 63% in this case, but still pretty damn high. In this case, different architectures are pretty clearly distinguishable. The fully connected networks are quite different. So these 2 branches correspond to augmentation and without augmentation. Again, the VITs have 2 branches, which is also augmentation and without augmentation. If you think about it, the truth in the test space is like the bull's eye that all these networks are trying to hit. A fully connected network doesn't go very close to the bull's eye. It has a large test error. So it is at a very large distance away from the bull's eye. A conv mixer or a large net in this case goes pretty close to the bullseye, so it is closer to truth. Okay, in this case, you can see the truth visibly, although the second, even if the second eigenvalue is negative still. Okay. Let's not worry about this plot. It's the same plot projected down. One thing maybe I will say is the cloud of fully connected models is all pretty clustered together. So fully connected models have, in this case, 40% error, but they are all making the same kinds of mistakes. The conv mixer models have about 4 or 5% error, I don't remember, but they're all correct in the same way, which is very weird. So we are training, this is a pretty large ensemble of networks, all said and done. They are learning in the exact same way, and they're making the same kinds of mistakes, which are primarily distinguished by the architectures that we have. Okay, this is a slightly smaller scale version on ImageNet. Things essentially look the same. The explained stress in this case is about 8.5 on the training set, and again 8.5 on the test set in the top 3 dimensions. Here is a more refined version, way to analyze this. Until now, we have analyzed the models that these networks represent. Now we'll analyze trajectories or training trajectories of different architectures. So given a sequence of waypoints, I take a network, I train it for, let's say, 200 epochs, I chop it up into or record the weights at different iterations, and I get a probability model for every instance, right? This is a sequence of checkpoints. We interpolate every consecutive checkpoints using the geodesic between them. So that's just a nice trajectory to interpolate them with. Okay, and you can get a continuous curve. But then if you want to now understand the differences between the continuous curve that corresponds to a fully connected network and a continuous curve that corresponds to CNN, it's not that easy to do it because different networks, they train at very, very different speeds. A CNN will get 50% error within the first epoch. A fully connected network will get 40% error after 200 epochs or 300 epochs. So it's not very easy to calculate distances between these trajectories. What we do is every trajectory that lies on the sphere, in the product sphere in this case, we project a point from that trajectory onto the geodesic. And so for this particular point, we assign a quantity called a time, if you will, the time of a particle that begins at P0 and travels along the geodesic at constant velocity. This is simply a technique to take these trajectories where particles are traveling at different speeds and give them a unique notion of time, corresponding to the geodesic and the unit velocity there. Okay. Once we map the time of different trajectories like this, we can now calculate distances. So the distance between two trajectories, which are continuous curves now, is simply the integral of the Bhattacharya distance of the slices of those trajectories at the same level of progress. So two networks, one of them takes 5 epochs to reach 0.1 progress, another one takes 50 epochs to reach 0.1 progress. I will slice them at the same level of progress and then calculate distances between them. And this is a pretty faithful way of looking at trajectories. Okay. And here is what we can do after this analysis. So we now took our data. Let's say these were all the 150,000 models. They correspond to about 2,300 or so trajectories. We have a pairwise distance between two trajectories. We can look at an MDS of this pairwise distance between trajectories. So in the previous pictures, I was showing you points where each point was a neural network. I will now show you pictures, or I'll show you analysis where each point is a trajectory. And you'll ask yourself, how different is one trajectory from another? So this is a dendrogram. You are not expected to read this dendrogram. What I want to show you is that each architecture has a different color, and trajectories of one architecture are similar to each other. The variations in this blue cloud are coming from different optimizer, different regularizers, and they're minor as compared to the differences between the blue cloud and the orange cloud and the red cloud. Okay, so differences between different optimization algorithms and regularization methods are minor. And this is a pattern that is consistent across the entire data that we have collected and the many experiments that we have been running over the last year or so. Architectures primarily distinguish trajectories. Yeah. If you kind of dig deeper into one particular architecture, then you will see differences in how the optimization algorithms behave. So all the Adam trajectories are close to each other, irrespective of what hyperparameters were used to train them. All the SGD trajectories are similar to each other, irrespective of what hyperparameters were used to train them. So optimization is the second most important one factor that we should be focusing on, and regularization is really the third. These kinds of things are folklore among practitioners. This is the first time where you can precisely say this is why, or this is how I quantify this particular folklore. Okay, we don't know why this is so, but you know that it is so. Yep. And here is a picture of the first two principal components of multidimensional scaling, where each point now is one trajectory of a particular network. All the fully connected trajectories lie pretty close to each other. All the conmixers are split into two clusters. This is they correspond to different augmentations. They are all quite different from the geodesic. Yeah. Here is another result that we really wanted. So we did all this analysis of the trajectories in order to get this particular result. And that it says that a large network and a small network, they travel along essentially the same trajectory. It is just that the larger network is a bit faster. So on the y-axis, I am showing you progress. Progress is the amount of time the constant velocity particle along the geodesic takes to reach the projection of a model on the geodesic. So it's how far up or how close you are to the truth is roughly the y-axis. The x-axis is epochs, the training epochs, okay? And a large ResNet in this case has a much larger progress for the same number of epochs. The trajectories of the large ResNet and the small ResNet are pretty close to each other over here, okay? So it's the same manifold that they live in, and just that the larger ones travel faster. So when people say that larger models work better, we should probably understand that statement a little bit as smaller models could also work as well if only we knew how to train them. Okay, so it's not as if there is something magical about over parameterization. It is probably our inadequacy in how we train the small models. There are some results in the literature where people have shown that larger models gain an implicit acceleration that comes from lifting style arguments, but yeah. For ImageNet, this result is a tiny bit milder. There are differences in how the yellow line is a bit ahead of the orange line, but you don't see them very well on this plot. Okay, a slightly different construction. You can take ImageNet. So the red line is ImageNet. I can again play the same game, train many models on ImageNet, and I get a curve, which is the red line. We trained different networks now on subsets of ImageNet. So there is about 118 dogs in ImageNet, and you can take a ResNet and train it only on the dogs and refashion it to make predictions on the remainder of the classes. This is easy to do by simply calculating the centroids of the features of the other classes. So you can take a network trained on dogs, make it predict not well, but ask it how well it predicts on the other classes, and that now makes it a network on the entire ImageNet. We can again put all these networks in the same space and ask questions about the space of tasks. Until now, we were asking questions about the space of models trained on one task. This is a three-dimensional embedding. It is again low dimensional, top three dimensions of models trained on different subsets of ImageNet. They all still live in what is effectively a 3-4 dimensional space. So not only do models trained on one task lie on a low dimensional manifold, models trained on many different tasks are quite different in this case: reptiles, birds, invertebrates, vehicles, and the entire ImageNet. They still lie in the same low dimensional space. The reason we do a good job of problems like fine tuning or transfer learning or meta learning is because we are working with this intrinsically low dimensional space. Okay. We did this cute experiment. This is the ontology of ImageNet, and this is how different phyla are. You can stratify them further down into different categories. This ontology was created simply using language. There's nothing to do with visual classification tasks. You can look at these trajectories, calculate distances between trajectories, and reconstruct this ontology. So the way the trajectories bifurcate while learning visual classification tasks is similar to how the ontology looks for language, which is inherent in the ImageNet classes. And obviously, we don't know why this is so, but this is pretty cool because that tells you that the two modalities have pretty strong shared connections between the two, between them, and we should be able to understand one from the other. Okay, using this kind of techniques, we also showed a few other things. For instance, meta learning and supervised learning learn the same thing, except that meta learning is very horrendously inefficient in how it learns things. Self-supervised learning and supervised learning learn the same thing, except that self-supervised learning doesn't go all the way to the truth. It stops midway because it doesn't know the truth. It only uses the proxy task. But they can use these kinds of techniques to ask many questions to typical methods. Okay, so here is a new picture, a slightly more refined picture of the previous manifold. The manifold of predictions of different networks. It looks a bit like hyperribbon. I showed you a very visible picture of this after the cartoon. Different tasks, they also project to similar parts of the manifold. This is why our models live in low dimensions after we embed them using MDS. And this is why a model trained on one task can predict pretty well on other tasks, because all you need to do is adapt the sloppy dimensions. You don't need to do very much to change the you don't need to change the stiff directions very much. Yeah, this would explain why we can do good transfer learning or we learn flexible representations. How much time do I have? Okay, so in the tiny time that remains, I want to show you a new result. This is a very peculiar and beautiful to me experiment. The statisticians will know this from before. We have said things about the structure of the prediction space. We argued that in spite of the gigantic dimension of the weight space, the predictions, they have very nice, well-defined structure. We believe this is because the task is sloppy, although we haven't really made that connection precise yet, beyond some toy models. I will next show you a way to exploit this structure secretly. And here is an experiment. So think of a very simple problem where you would like to estimate the bias of a coin. I give you a biased coin. You are allowed to do lots of coin tosses and estimate the bias. If I allow you a lot of coin tosses, then you, if you're a Bayesian, you will put a uniform distribution between on 0 to 1, toss your coins, and then wait for the posterior to localize and give me the mean of the posterior, let's say, as the solution. This is nothing special. The fact of the matter is that you put your probability mass on an infinite set of models. That is why you need a lot of samples to localize among this infinite set of models. If I only allow you one coin toss, what prior should you pick in your experiment? You're only allowed to toss the coin once instead of as many times as you want. And this is a pretty classical question. And the way to think about this is that I allow you only one bit of information to distinguish things. With that one bit of information, the one coin toss, you can only distinguish two things. Okay. Now, so the real question here is which two models are you going to put your probability mass on as the prior in order to get a good estimate? Yeah. You don't know anything about what the coin is. You do know that the coin will either come out heads or tails. So those are the two outcomes that you should put your mass on. This is the subject of what is called a reference prior. So reference priors are very classical things in what is called objective Bayesian priors. They were built in the 70s. And I'll tell you about it next. So Yansong Gao is finishing his PhD with me. He'll be graduating this summer, and he's looking for a postdoc. If you folks have jobs, he has some very beautiful work in understanding the space of tasks. And we can do pretty cool things. So in the picture that I showed you, I did not the correct way to go from one endpoint of the green trajectory to an endpoint of the red trajectory is a geodesic in this space. Is the best way to transfer between two models. We can play a lot of games like this. So Yansong has formalized in some sense the correct distance between tasks and the right way to do transfer learning, or the optimal way to do transfer learning. We can give algorithms with pretty spooky guarantees. So if you have a model that has 95% accuracy on a source data set, we can devise an algorithm that also gets 95% accuracy on a target data set, formally speaking. And we can also instantiate the algorithms, of course, but it's a very interesting mechanism where we modify both the model that is being fine-tuned or transferred and the data set itself, and anneal the data set from the source to the target. So we have a pretty nice characterization of the space of tasks, and we can play these games across that. Yeah. That's a reference prior. So reference priors are formalized as follows. So you would like to find a distribution on the weight space that corresponds to this prior. And one way to think about this is that if you give me few samples to choose from, in this case, you have n samples to use to perform your inference, then you want if n is small, you want the posterior to be maximally dominated by the data. You don't want the posterior to be dominated by the prior. It's a slightly different way than how a machine learning person thinks. Machine learning person would like to take the prior and bias the solution using the prior, because we presumably know something about the kind of data that we're dealing with. But if you have very few data, then you better trust the data. There is nothing else that you can do. So a reference prior is something that depends on the distribution of data and the number of samples that you're going to get at inference time, nothing else. And you're maximizing the KL divergence between the posterior W given your n samples and the prior pi of W on average over the samples that you're going to get. So to calculate this, you need two things. You need some estimate of the distribution of data and n that you want. So if n equal to 1, as I motivated before, the reference prior has two atoms, one on 0 and one on 1, because those are the boundaries of the manifold of models. And these are the two most distinct outcomes that you will get after you toss the coin. If I give you more coin tosses, then the reference prior grows more atoms, and they're all equidistant from each other in the space of distributions. As I give you an infinite number of samples, the reference prior converges in one dimension. This is precise to the Jeffreys prior. Okay, so everything is nice. It is not spookily different from what we know. It is basically a different way of thinking about Jeffreys prior for finite sample sizes. Yeah, here is how the reference prior looks. So what we did is we took a binary classification problem on MNIST. We fitted a reference prior, so you can prove that the reference prior is always supported on a finite number of atoms. For any finite number of samples, there is a finite number of atoms in the reference prior. The number of atoms typically grows quite quickly. So if you have n samples, the atoms are roughly n raised to 4/3 or so for a Gaussian model. But the fact of the matter is it is atoms. Now, once you have the atoms, you can run Blau Tarimoto to optimize the locations of these atoms. So what I'm showing you here is every point, again, is one neural network. They all began this optimization problem at these blue locations, which is where this is again like the MDS version. They all began the training at optimization at the blue locations. And as I maximize the mutual information, they all began spreading out. Just like in our coin tossing example, the two atoms are maximally distinct from each other. The green points are traveling further and further away in the space of probability distributions. They do not know what labels they are predicting. So one of them will take an image and it will call it red. The other one will take an image and call it a giraffe. And they are all trying to be distinct from each other in as many ways as possible. Okay, there's about 3,000 atoms here for MNIST. So in a schematic, we have the manifold of predictions. The atoms of a reference prior are maximally different models on this manifold. So these would correspond to the boundaries and the corners of this manifold. You wouldn't be able to instantiate a reference prior like I did if the manifold were not low dimensional, because then you will need to you will suffer the curse of dimensionality. You will need to put lots and lots of atoms. In this case, we can do this experiment even because the manifold is such low dimensional. Okay. Jeffreys prior would put a lot of mass in the interior of the manifold, and that is why it is inefficient when it comes to small sample sizes. The way to think about this is that these atoms are very different from each other. So when I show you some label data, one of them strikes gold, and that dominates the posterior. Okay. So for classification, it looks a bit like this. So you're again maximizing mutual information between n samples, their outputs, which you do not know yet, and the weights. And if you write it down, it will look like the difference in the entropy of the marginal distribution y given x over all the atoms of the reference prior, and the entropy of each of the atoms of the reference prior. So in some sense, this is the one that you're maximizing this. So you're minimizing the entropy of the predictions of each atom or each model. Each model likes to be confident, but all the atoms like to be confident in different ways, which is the first term. And that is why they are doomed to be diverse in the space of distributions. Okay. If you peer at this very carefully, you can think of it as a theory for self-supervised learning or semi-supervised learning. And what we did in this paper is we can show that roughly there is a lot of ad hoc techniques in self-supervised learning today. We can take all those techniques and derive them from this objective. So in some sense, this objective is the union of all the tricks And people did not quite know this objective, so they implement all the tricks, but you can show that the union of the tricks is the same as this objective. So then that is why I like to think of it as a theory for self-supervised learning. It also works about as well. So on CIFAR with 50 samples, you can get about 85% accuracy, which is competitive with the best methods that we have for semi-supervised learning today. Okay, there are beautiful connections of this to like systems biology and predictive coding. We don't have to worry about them right now. But let me conclude with the following two remarks. So I think the success of deep learning is telling us new things about data, and that is why we should pay attention to it. In our effort to understand these networks, we have really attributed terribly many magical properties to them. We do that every single day. My Uber driver yesterday spent half an hour telling me about AI. So clearly, everyone who is not necessarily a researcher is also interested and curious about these things. But it's a statement about the world we live in, not necessarily the models of the world that we live in. Deep networks, after all, are models of the data. Now we have a different microscope, a new microscope that allows us to look at data in more interesting ways, and we should be understanding more about the data. Okay. The second one is a bit more philosophical. So it is very surprising to me why there is such strong structure in natural data. It is very surprising. The way a physicist would think about this is there are ideas like renormalization group theory in physics, which try to pluck out structure from microscopic degrees of variation. And they work for very special reasons or very special cases. So I take this podium and there is a microscopic level disorder between the molecules here, and together they come and give us properties like stress, strain, shape, etc., which are low dimensional functions of the intrinsic variability of this big ensemble of particles. So in physics, we know when such properties should arise. They shouldn't arise for any system. They should arise only if we do not care about asking questions to the data of where the locations, where the molecules are at this particular instant. I don't care where the molecules are. I'm only interested in the stress. And this is why you're allowed to think of the object as a low dimensional object. If I wanted to know the locations of the molecules, you would have to build a different kind of theory, the one that goes one level below the classical one we studied in high school. Okay, so in physics, structure emerges because we choose to ask questions at a different level of granularity. That's a question of physics. When you think about understanding learning, after this became an object, we choose to give it semantic attributes. The kind of attributes that we give to objects are not arbitrary. So you call a cat because you choose to remember all these molecules using this one simple code word. You don't care about counting leaves on a tree unless you're very peculiar. So those kinds of problems are hard for us, and they are hard because this is more information that we need from the input. So we learn problems that are learnable, and we ignore the rest, is how I would like to think about it. And the ones that are learnable were created by us to begin with. Shouldn't be a big surprise why a computer can learn them easily. I will stop here and take questions. Mm-hmm. No, so the data definitely looks like this for essentially all data that I have tried. So the way I say it is, if you show me a data set that doesn't look like this, I buy you beer. I haven't bought one yet. Architectures will, so different data sets will differ in the slope. For instance, if you have many classes, the slope is a little bit shallower, and there you do see the curse of dimensionality when you fit these models. So sloppiness is a statement of why we can get away with few samples. If the spectrum was decaying like this, then it would be a genuinely easy problem. If the spectrum was more shallow, then you would see the curse of dimensionality. Architectures don't seem to affect much. So for instance, the model at the beginning of training has a spectrum that is not sloppy. After all, it is initialized randomly. And as it trains, it becomes closer and closer to the orange line. There should be, yes, I believe there should be differences, and you will see in the calculations that there are differences, because in this particular theorem, we've assumed that it's a positively homogeneous nonlinearity with slope 1 at 0. The eigenspectrum is a very coarse way to look at these properties, so we may not see it.
How after architecture and observation.
Yeah, so yeah. So if you zoom into one particular cluster, I'm zooming into this particular one here, you will see that trajectories of Adam, SGDN are all clustered together. Between the cluster of Adam trajectories, these are, this is the batch size, this is the learning rate, this is the weight decay, this is the augmentation. You don't see very big differences. So this is an experimental result that says that optimization doesn't seem to change the function that you learn during during training. I think these are all first order methods. So second order methods would look very different from first order methods. But conditional on you being a second order method, again, like it will be a similar picture, I believe.